Okay, so here's our first problem. Our first related rates example is about this pebble where you plunk it into the water and it makes some ripples, right? So the first step, it says a rock is thrown into a smooth pond, creating a circular ripple that spreads out at a rate of 0.5 feet per second. And then it says how fast is the area of the ripple growing when the radius is 3 feet. Okay, so the first step in solving a related rates problem is traditionally going to be to draw some sort of picture and assign some variables. Okay, so in this particular thing, I'm going to draw a circle because it's a circular ripple. And I realize I'm drawing in front of my face, so I move here. Draw a circular ripple, and if you think about what's going on here is this ripple, it's growing, right? So what's changing? The radius. We probably identified that in our earlier on the Desmos screen. The radius is changing, right? And so I've assigned the circle. I've drawn the circle here, and I've assigned this variable r. Okay, and now the next step, once you have a picture and some variables assigned, is what I like to do is identify the nose and the once. The nose and the once. Okay, so in this particular problem, I am being told here that the rock is thrown into a smooth pond, creating a circular ripple that spreads outwards at a rate of 0.5 feet per second. So I see that feet per second, and that tells me that I know that dr dt equals 0.5 feet per second. Okay, I know that dr dt equals 0.5 feet per second. The radius is measured in feet and time is measured in seconds. So that was sort of one insight as to knowing that was dr dt. Okay, the radius is changing at a rate of 0.5 feet per second. Okay, and what do I want to know? Okay, the question says, how fast is the area of the ripple growing when the radius is 3 feet? So there's always going to be a when. How fast is this changing when? It's like, we have this situation going on here. The radius is changing. The ripple's getting bigger, blah, 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 blah. And as soon as the radius gets to 3 feet, we take a picture and take a snapshot and say, okay, how fast is the area changing at that instant? All right, and so what's our want here? I want to know dA dt. A stands for area. And when do I want it? When r is 3. Okay, so I've identified my nose and my once. Okay. The next step is traditionally going to be to find some sort of equation that relates these variables, a and r. Okay? Maybe there's a t in it, maybe not. Okay? But find out some relationship that relates these variables that are in the numerators of your derivatives, like a and r. Okay? So is there some sort of equation that relates a and r in this situation? Well, of course. It's a circle. The equation of the area of a circle is pi r squared, right? So here's a relationship between a and r. All right? Next step is differentiate that equation with respect to t. Okay? So in this case, the derivative with respect to t, is just going to be dA dt. And if we were writing this using the chain rule, dA dt would be equal to dA dr times dr dt. Okay? And what's dA dr? Well, dA dr is just going to be 2 pi r. And then times dr dt. This is also, it's implicit differentiation. It's the chain rule. It's the same thing. But that quantity right there is dA dr. Okay? 2 pi r is how the area is changing with respect to the radius. dA dt is how the area is changing with respect to time. Notice that time is nowhere mentioned here. There's no t's anywhere. The only place that it identifies something that involving time was that initial rate that we were given. Okay? And so now I've got this expression, dA dt equals 2 pi r times dr dt. Okay? This has the variable I want in it right here. It has the variable that I know in it right here. And there's also some other stuff here. So at this point we have sort of an option. And sometimes I'll do this both ways. We can solve for the variable that we want, and then substitute in the things that we know, or we can substitute in the things that we know and then solve for the variable that we want. In this case, I'm going to go ahead and it's already solved for dA dt, so I'm going to calculate what's dA dt now when r equals 3. So I just plug in 3 for r, and then I multiply by whatever that dr dt value was that I was given. That's a constant, 0.5. It's not changing. I could put 0.5 per, feet per second there, but I won't. Okay? And so after I do this arithmetic here, I get 3 times 2 pi is 6 pi times 0.5. So that looks like 3 pi. Okay? So now the question is, it's very important here, what are the units of this number right here? This is how fast the area is changing with respect to time. So what are the units of that? Well, the units of area are feet squared, and the units of time in this particular problem are second. So that's 3 pi feet squared per second. Now, if you wanted a decimal for that, I don't know what 3 pi is as a decimal, so we'll break out big red here. So 9.42 and some change. So let me put this into a context here, okay? This circle is getting bigger and bigger and bigger. As soon as the radius gets to 3, we snap a picture. And at that instant, the area is changing at 9.42 feet squared per second, okay? If the radius was always changing at a rate of 0.5 feet per second, okay? So that's question number 1. Make sure you get all this down. Okay,